Hi everybody, this is chapter 11. We are going to look at surface area and volume in this chapter. Our first section is section 11.1, and we're going to look at solids and then their cross sections as well. All right, when we talk about solids, we're going to talk about polyhedrons. They are three-dimensional figures, and the surfaces are made up of different polygons. Each polygon is a face of the polyhedron, so think of like a box. Each surface is a face. Where the faces meet, that is considered an edge. It's a segment that is formed by the intersection of the two faces. And a vertex is where three or more edges intersect. So just think where the corners come to, or the corners of the figure where the sides or the segments come together. The plural of polyhedron is polyhedra. And polyhedrons enclose regions of space. All right, so if we look here, we have a rectangular pyramid because we always name a pyramid. This is a pyramid because it comes to a point here at the top. You name a pyramid by its base. So I'm going to assume it's a rectangle. Again, I might be off on that. It's a quadrilateral, so most often it's a rectangle. And we're going to identify our vertices first. We have 5 of them, and those are D, so vertices again are where the edges come together, E, F, G, and H. The edges are where the faces come together, so we have DE here, EF right here, FG, GD, and then we have DH, FH, GH, and then also they missed one. We have EH as well. And then the faces are 4 triangles because your faces are what makes up the sides. So we got triangles here. And then we got our base, which is our rectangular bottom or our quadrilateral. All right, next we're going to talk a little bit about Eulers Formula. And Eulers Formula says that the sum of the number of faces and vertices of a polyhedron is always 2 more than the number of its edges. So again, faces plus vertices equals edges plus 2. All right, so if we look at this, we're using Euler's formula to figure out how many vertices, edges, and faces this has, and then verify Euler's formula with it. So faces, remember, are like the surfaces. So we have 2 bases. So 1, 2. So, and then the sides holding up the bases. So this will be 1, 2, 3, 4, 5, and then this one right here would be 6. So the 2 bases plus the sides would make it, we have for our faces, it's equal to 8. All right, and then next, let's look at vertices. Those are your corners. So we're going to do vertices is equal to, and then we have 1, 2, 3, 4, 5, 6. And then on the bottom, we have 6 more. So 1, 2, 3, 4, 5, 6. So together, 6 plus 6 is going to give me 12 vertices. Edges are always, the sides where the 2 faces come together. So we have 1, 2, 3, 4, 5, 6 going around the outside. But then we also have 7, 8, 9, 10, 11, and 12. And then the bottom, 13, 14, 15, 16, 17, and 18. So edges is going to be 18. If we look at Euler's formula, remember it was faces plus vertices is equal to edges plus 2. So if I do 8 plus 12, it's going to be equal to 18 plus 2. And that does work out because 8 plus 12 is 20, and 18 plus 2 is 20. All right, so here we have 3 polyhedrons shown, or we have 3 solids shown, and they want us to identify which one is a polyhedron. So remember, a polyhedron has all faces that are polygons, and polygons are made up of line segments. It's a closed figure. So if I look here at this figure right here, it's a sphere. It's not made up of line segments. It's made up of, it's a circle for a base. It's circular. So this is not a polyhedron. And then the same thing with this shape here. It's a cone. It has a round base, which is not made up of line segments. So the first polyhedron, or the first figure here, is the only polyhedron on this page. All right, a cross-section is the intersection of a solid and a plane. So it's like if you were to take a figure and slice it, either vertically or horizontally, you would get a cross-section. So here we have a triangular prism, and they cut it vertically. And the cross-section, you can see if I highlight it, is going to be a triangle there. And your cross-section depends on how you cut the figure. Again, if you go vertically, it may be one shape. If you go horizontally, it may be another. So here we have a cylinder. It has a circular base. It's a solid. It's not a polyhedron. But if I were to cut it vertically, notice if we highlight this cut right here, it's going to make it a rectangle for the cross-section. But if I cut it horizontally, my cross-section is a circle. So it does matter how you cut it. I say vertical or horizontal. They call it perpendicular or parallel to the bases. All right, cross-sections are important because they are used a lot on topographic maps. A topographic map or a contour map, it shows elevations or contour lines. And then detailed physical characteristics of a landscape. I just recently bought a house, and it was a new house we had built, so when we saw the site plans, we could see the lines for elevation to show the varying, like the backyard is not totally flat, so I could see how much, it was going to slope a little in the back. And you can kind of see here, if we look at this map, all the different elevations available for the mountain or the hill that they're looking at. So each, the more your lines are closer together, or they tend to be really close right here, the steeper the side is. The further apart they are, the flatter it's going to be. All right, so if we are reading this map and they want us to know which hill is greater in elevation, either Ace or Bunker, if we look here, we can see they both start out at 10 feet, or 10, meters in elevation above sea level usually. But Bunker Hill goes only up to 40 meters and Ace Hill goes up to 50. So Ace Hill has the greater elevation. All right, now here, when they look at Ace Hill, they want to know which side, either north, south, east, or west, is the steepest. And again, we talked about the closer the lines are, the steeper your elevation is, the more they're spread out, the flatter the land is. So if we look where they're closest together, would be on this side, which if we look at our compass here is going to be the west side. So the west side of the hill is going to be the steepest. All right, so the last thing we're going to look at is just rotating a solid. So if we start off with, if you notice here, we're starting off with a rectangle, and we were to rotate that rectangle about line L. When we do that, the rotation will result in a cylinder. So if you want, take a piece of paper, tape it to a pencil and rotate it so you can see that cylinder shape. And our last figure that we're going to rotate, we have a triangle here. with the point or the one angle pointing down. And when we rotate this about line L, you're going to end up with a cone for your solid. And that is it for section 11.1.